Welcome back to lecture series on control systems. So this is the 10th video lecture, and actually from the 9th video onwards we were discussing, from the 8th video onwards we were discussing module 2 and module 3 together, because in some portions we may be jumping from module 2 to module 3, or we may be jumping back from 3 to 2 for getting some sort of continuity. It's purely my order. I hope it may help you also. Anyhow, today we are dealing something related to stability. In last class, what we did is we identified the pole zero plot from the transfer function. From the transfer function, we can identify which are the poles or which are the zeros. Generally, in those example, by marking the position of poles, we can say whether the system is stable or not stable, unstable. If we are just recapping that, if one pole lies on the right hand side, the system will be, this is my question, it may have several poles on the left side. I don't mind that. But among that, if one pole is located on the right half plane of the S domain or J omega axis, then the system will be unstable. So we don't mind how much poles are there at the left side. If any one of the pole is located at the right side of J omega axis, system will be definitely unstable. And if there is one pole in the J omega axis, on the axis itself, I am not talking about the right side or left side. For example, if one pole is plus 2j and other pole is minus 2j. Plus 2j means its imaginary part is 2j, its real part is 0. So it lies on the axis 0 plus 2j and 0 minus 2j. So plus 2j minus 2j or 2i minus 2i, these poles will lie on the imaginary axis. If a transfer function is having 3 poles on the left side and the remaining 2 poles are placed on the J omega axis, what happens? 3 poles are there on the left side, but only 2 poles lies on the J omega axis. What happens? If you have doubts, you should go to the last lecture and please clear these things. So the answer is, how much poles are there on the left side, I don't know, but if 2 poles are on the imaginary axis and no poles are on the right side, we have to say that also. No poles are there on the right side. 3 poles are on the left side and 2 poles are on the imaginary axis. Then the system will be marginally stable. We explained the concept of marginal stability very well in last video using Bebo stability. It is the hardcore concept of control system. So I hope you will watch it. And now, in the same example, if I am having 6 poles, 6 poles mean order of the transfer function will be 6. The equation will be s raised to 6 plus something into s raised to 5 plus, like that. Or if you are arranging in s plus form, it will be s plus p1, s plus p2, s plus p3, like 6 terms will come. Okay, so anyhow, if the transfer function's denominator is having order of 6, suppose 3 poles are on the left side and 2 poles are on the imaginary axis and 1 pole is on the right side. I will repeat it. 3 poles are on the left side, 2 poles are on the imaginary axis. This is the imaginary axis. And remaining one and only pole is on the right side. Is the system is marginally stable or unstable or stable? Whatever may be the condition, how much poles may be on the left side, however, how many poles will be there on the imaginary axis, I don't mind. If any one of the pole is on the right side, system will be definitely unstable. That is the condition. Okay. So, now in the last class we discussed broadly about these all things, how we can comment about the stability by drawing the pole, by marking the poles from the pole zero plot, or we can also find I of t, response of output y of t, and we have to put some input y of s is equal to u of s into r of s. Then plan transfer function into y of s is equal to plan transfer function into input u of s. You can substitute any of the input and whether check the output is bounded or not. Like that, in that method also you can find the stability. All those things are there in the previous lecture. Now today's class we are going to RH stability criteria. ROUTH HURWITZ is the man who discovered this. ROUTH HURWITZ stability criteria. In ROUTH HURWITZ stability criteria, we don't need to go for these response y of s, and we don't need to convert it to y of t. Don't put some arbitrary inputs. Don't need to do all this calculation, or even you don't need to bother about the location of poles also. Without bothering all these things, you can comment about the stability from transfer function by doing some simple mathematics. That is the advantage of ROUTH HURWITZ stability criteria. And also, ROUTH HURWITZ stability criteria will say you how much poles are located at the left side, how much poles are located at the right side, is there any poles around the j omega axis. All the location of poles will be given from the transfer function itself. Suppose, okay, we will discuss it in detail by slides. So, ROUTH HURWITZ or RH stability criteria. If u of s is input, y of s is output. That is the general representation. U of s is input, y of s is output, and be sure that we are representing things in S domain. So g of s is the forward transfer function of plant, and h of s is the feedback function. So if we are finding the closed loop transfer function, we know that it is whether it is positive feedback or negative feedback. Yeah, so you can see here it is a negative feedback system. Feedback is given to negative. So C of s by R of s is G of s by 1 plus G of s H of s. Okay. Suppose the system is, this is the standard form, but I don't know whether the system may having a number of blocks, the feedback path may have some gain. Okay, anyhow, if you are solving this all by using block diagram reduction, or by finding the transfer function from modeling of mechanical system, anyhow you will get a transfer function that we can write in form of C of s by R of s. If it is given directly, G of s is given directly, H of s is given directly, you can find by using G of s by 1 plus G of s H of s. Anyhow, that transfer function will be in the order of, will be in the standard form of this equation. Don't get confused by seeing such a big equation. Normally in our equation, poles will be present and zeros will be absent. That's why in all the transfer function we discussed in last class, the numerator was 1 by s plus 2 into s plus 3, like that. That means zeros may be present in some other case. In all case, it may not be like 1 by s plus 1 into s plus 2. It may be s plus 2 by s plus 1 into s plus 2. Please be clear. If a transfer function is given, C of s by R of s is equal to s plus 2 divided by s plus 2 into s plus 3. Please write it in your notebook. S plus 2 by s plus 2 into s plus 3. What is the poles and what is the zeros? The numerator will give zeros and denominator will give poles. Equate the numerator is equal to 0. What is there in the numerator? S plus 2. So equals s plus 2 is equal to 0. Then s is equal to minus 2. That is the one and only 0 of that case. So zeros may be also present in your problem. You don't take always the numerator will be 1. It is not like that. In most of the cases numerator may be 1, but it is not a condition. Okay, in that example I said that s plus 2 by s plus 2 into s plus 3. Okay. So if you are equating denominator is equal to 0, s plus 2 is equal to 0, s plus 3 is equal to 0, you will get s is equal to minus 2 and s is equal to minus 3. So the poles are minus 2 and minus 3. That's why in this case I am representing it instead of 2 and 3 such values, we are standardizing s plus z1, z1 means 0, 1, s plus z2, z2 means 0, 2 and so on. I don't know. It may be n numbers of poles may be, zeros may be present. So we can write that s plus z1, s plus z2, dot 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 up to s plus zn. That is the correct thing. And pole may be, in standard representation, poles may be n numbers, s plus p1, s plus p2 up to s plus pn, n number of poles may be present. Okay, so the example we considered last was s plus 2 by s plus 2 into s plus 3. So what is the order of this transfer function? Or what is the order of denominator of the transfer? Let us leave the numerator. Zeros, we are not discussing that much concentratedly now. Now we are concentrating only on poles or denominator. So s plus 2 into s plus 3 is the denominator. So poles are minus 2 and minus 3. What is the order of that transfer function or order of that particular denominator? That is 2, because if you are opening the brackets, it will give s plus 2 into s plus 3. If you are opening the bracket, what it will give? Please try. S square plus 5s plus 6. So degree of higher order term is 2, s square. So it is a second order term. Or simply if there is 2 poles, it is second order. If there is 3 poles, s plus 2 plus s plus 3 plus s plus 1, then it is third order, 3 poles. And if you are opening the brackets, it will give s cube, like that. If there is n poles, then if you are opening all the brackets, the denominator will give s raised to n plus something will be there. So like that, we can say the order from the standard differential equation, or you can specify the order from the pole arrangement, s plus p1, s plus p2. From both these representation, we can easily identify the order of the denominator. Now, if denominator of C of s by R of s is equal to 0, that equation is known as characteristic equation. That is, we are only talking about the poles from now onwards. We are just avoiding the denominator. We are only discussing about we are avoiding the numerator. We are only discussing about the denominator. So s plus p1, s plus p2, that term we are discussing, and that should be equal to 0. Denominator of the transfer function should be equal to 0. That is known as characteristic equation. And don't forget to put this 0. If you forget to equate that to 0, it will be entirely meaningless. Okay, we'll see. Now, roots of characteristic equation is equal to poles. That is also clear. In the previous case, the example was, we are always dealing that example on today's class. So please memorize that. S plus 2 by s plus 2 into s plus 3. So if you are open the brackets in the denominator, it will give s square plus 5s plus 6. So what is the characteristic equation? S square plus 5s plus 6 is equal to 0. That is the characteristic equation. S square plus 5s plus 6 is equal to 0. That is the characteristic equation. Then roots of that equation is, if you are solving that equation, you will get s plus 2 into, you will do the back steps. S plus 2 into s plus 3 is equal to 0, s is equal to minus 2 and minus 3. So that are the poles. So what is the conclusion? If a characteristic equation is directly given to you, its its roots will represent the poles of the transfer function. Its roots will represent poles of the transfer function. That is the case. Now, RH criteria. The advantage of RH criteria, I already discussed these things in the introduction itself. The advantage of RH criteria is that you don't need to draw a pole through plot, no need to do any other complicated calculation like Laplace inverse, such things are not needed. RH criteria gives number of right side poles of a transfer function without solving it. If you are getting a complicated transfer function like s raised to 5 plus 4s raised to 4 plus s cube plus 2s square plus 1s is equal to 0, it is not that easy to solve it like s plus 2 into s plus 3, because it is a fourth order or fifth order equation. Fractionalizing is somewhat difficult. To find the factorial is somewhat difficult. In such case, if you have RH stability criteria, you don't need to solve the transfer function with or characteristic equation without solving. You can easily find how much poles are there on the right side, how much poles are there on the left side, and you can easily understand whether the system is stable or unstable. Once more, what is the condition for instability? Even at least one pole is present on the right side, the system will be unstable. Okay. Now, let us consider a characteristic equation. 1 plus g of s h of s is equal to 0. I hope you will get how that came. Generally, what is our closed loop transfer function? G of s h of s by 1 plus g of s h of s. Okay, and we are equating its denominator is equal to 0. That's why we are directly taking 1 plus g of s h of s is equal to 0. So don't get confused. Use a paper and take an example of g of s and h of s, and you can solve it. Suppose g of s h of s is equal to some value. You can find the transfer function by using c of s by r of s, or g of s, or by using the standard equation g of s by 1 plus g of s, and you will get the transfer function and its denominator, equate its denominator is equal to 0. And please check whether 1 plus g of s h of s is equal to 0 is also giving the same answer. It will give the same answer. Okay, you don't need to do all the things, but the issue is 1 plus g of s h of s is equal to 0 means there you will get a denominator and that will cross multiply. That is the case. If you are taking characteristic equation from transfer function, you should say that denominator of transfer function is equal to 0. Here you are not taking denominator, you are just taking 1 plus g of s h of s is equal to 0. So its denominator will be equated, cross multiplied, and that will also equal to 0. Anyhow, please check that these two conditions will be same. Anyhow, the transfer characteristic equation is a0 into s raised to 4 plus a1 into s cube. It is a fourth order transfer function and I don't know the coefficient, that way I am taking arbitrary values a0, a1, a2, a3, a4 like that. So a0 into s raised to 4 plus a1 into s cube plus a2 s square plus a3s plus a4 is equal to 0. That is the characteristic equation. And I am going to apply RH stability criteria on this characteristic equation. So this characteristic equation, how we got this characteristic equation? There is two ways. I already told you. Find c of s by r of s or g of s by 1 plus g of s h of s and take its denominator is equal to 0. Or directly do 1 plus g of s h of s is equal to 0. Both will give same equation. So before applying RH criteria, I have two important conditions to check. This is the very important condition. Normally in exam point of view, they will not leave you by checking and failing this condition, because if any one of these condition fails, you don't need to apply RH criteria, because if this condition fail initially without applying RH criteria itself, you can say the system is unstable. So in university exams, they will not permit you to do like this. They will have to apply RH stability criteria. But in some gate problems and all, we can see some big transfer function will appear and they will ask whether it is stable or unstable. So if you are not checking these two conditions and you are directly applying RHstability criteria, you will be misled. You don't need to apply RHstability criteria because in some problems, if these conditions are not satisfied, then on the point itself we can say the system is unstable. No, don't apply RHstability criteria. From this condition itself we can say system is unstable, like that. So before applying RHstability criteria, we should check whether the conditions are satisfied or not. First condition, all the coefficients in this equation, which are the coefficients A0, A1, A2, A3 and A4. A4 is also a coefficient because that term is s raised to 0. A3 s raised to 1 plus A4 s raised to 0. That is the concept. So all the coefficients should be of same sign. We are not suggesting all should be positive or should be negative. If A0 is positive, A1, A2, A3, A4 all should be positive. If A0 is negative, all should be negative. There should not be any sign change. That is our condition. All the coefficients, if you are drawing a graph, all the coefficients should lie on either on right side of real axis or left side to 0 on the real axis. All the coefficients should be either positive or either negative. A mixer is not permitted. If A0 is positive, A1 is negative and A2 is back to positive, such a combination is not permitted. This is the first condition. All the coefficients must be on the same side of real axis. Next, there should not be any missing coefficients. What is the meaning of missing coefficients? In that equation, suppose this term is not there. Suppose this term is not there. The equation is A0 S4 plus A2 S square plus A3 S plus A4 is equal to 0. This term of S3 is not there. The A1, this coefficient will be missing. All the S terms should be there in the equation. If it is a fourth order equation, S raised to 4 will be there, S cube will be there, S square will be there, S will be there, and the constant also should be there. Otherwise, we have to consider there is a missing of coefficient. If any one of these coefficients, A0, A1, A2, A3, any one of the coefficient of S term is missing, no need to apply RHstability criteria. You can directly say the system is unstable. Okay. If the above two conditions are satisfied, then the stability is tested by using RHstability criteria. So, be very careful from this point onwards. If you are with sharp-minded and that much concentrated, it is a one-time discussion. You will not forget in your entire life. For me also, I had studied the RHstability criteria very back. Even though I forgot many of the concepts related to control system, if I am not handling the subject for 3 or 4 years, but I didn't forget RHstability criteria's pattern because that is somewhat interesting pattern. So please be very careful in this topic. I am 100% sure that this will give you some marks in your university exams because it's such an important topic. Okay, now check the characteristic equation. I have written some in blue color and some in red color. That is the first point. A0 S raised to 4 is written blue and I written A1 S cube into red and again A2 S square into blue, A3 S into red. That alternating combination is required for us. That alternating combination of degrees is required for us. Please check the RH tabulation. This is the RH tabulation. Here I have written the highest degree S4 first, then S cube. Then I will write S square S1 later. Anyhow, S4 is the highest degree. I have marked that initially S4. Okay. And the degree of S4 is A0. Then I will take the other blue. I will leave the next degree and I will write a square. Again I will, sorry, not a square, a2. Again I will leave this a3. I will take the alternate coefficient, that is a4. So you can check. All the blue colors are marked a0, a2, a4. And I have consequently left all the blue things, or consequently left all the alternate coefficients. Now we are going to mark S3. In S3, I have to write coefficient of S3 first, that is A1, not S3, S cube, S raised to 3. A1 first, then the left combination A1, A3, and is there anything after that? No. Up to A3, everything is complete because A4 is already there in the top row. Now there is no coefficient after that, so simply write 0. Is it clear? First, A0, A2, A4, one combination by A0, A2, A4. I have left something here. Then take the left combination, A1, A3. It's over, and as there is nothing to write beneath the A4, I have put the 0 there. This is a simple thing, very, very simple thing. Okay, now I have to fill the S raised to 2 row. Let us check. Yeah. S raised to 2 row. What I have written there? A1, A2 minus A0, A3 by A1. Can you guess how I got this combination? Can you identify some simple pattern? Yeah, there is a beautiful pattern. I will explain. Look it. A1, A2. Please, A1, A2 minus A0, A3 minus A0, A3. It's just like a multiplication symbol. Should start from the lower side. A1, A2 minus A0, A3 divided by the starting point. Divided by the starting point means A1 itself. That is the case. Please make it by heart, or store it in your mind that you will never forget in your life. Store it like that. Be sure about it. Be sure about the technique. Okay, let's fill the next position in the column. Sorry, in the row. We are going to find this position. So, do you have any guess? Do you have any guess? Again, start from the same point. Same point means again start from A1. But don't write to A2, write to A4. A1, A4. Okay, A1, A4 minus A0 into 0, all divided by the starting point A1. Let us check. Yeah, I will repeat once more. A1, A4, A0 into 0, all divided by initial point A1. Is it clear? Is there anything after that? Is there anything in the third position of the row? Because if you have to write something, you have to multiply A1 with the other portion. Is there anything here? Nothing is here. So you have to write 0. A1 into 0 minus A0 into 0 by A1. So the entire term will become 0. You can see the entire term becomes 0. And now I am naming it. For the easiness, I am naming this total term as capital A and this total term as capital X. Okay, let it. Now we have to fill the column of S raised to 1, this column. So please, how we can fill this column? Start from this point. So this is the column just above, sorry, row just above. So start from here. This how you will get this equation that I am explaining. Start from here. A into A3 minus A1 into X. Just the same procedure. A into A3 minus A1 into X divided by the starting point A. Is it understood? I hope I'm making some sense. If no, you can contact me or you can ask doubts in the channel itself. Okay, anyhow, I am giving a name capital B because it is somewhat bigger. That's why I'm giving some small names only for the analysis only. If it is numerical values, no need to give such names. We can directly solve it. Okay, and what will be the equation here? How we will get this expression? How we will get this expression? You have to start from here and go to this portion. A into 0 minus A1 into 0 all divided by the starting point A. Anyhow, that whole term will become 0. So you have to write 0. And here also, previously you got 0 here. Likewise, here also you will get 0 as a third row. Now you got first row, second row, third row A and X 0, fourth row B and 0 and 0. Hope things are clear up to this moment. Now we will go to the last one, S0, last row. So for that S0, okay, we will discuss from here itself. For getting the S0, what we have to do? We have to multiply B into X minus A into 0 all divided by A. Yes, B into X minus A into 0. Oh, sorry, all divided by B. All divided by B. This is the starting point. This is the starting point. We can repeat once more. B. Its name is B. B into X minus A into 0 all divided by starting point B. Like that. What about the second term in the row? For getting the second term in the row, you have to write B into 0 minus A into 0 all divided by B. Anyhow, that term will become 0. And after that, we know that there is no possibility for getting any terms. So simply put 0 in the last column. I hope this is clear. So please make sense, or if you are having doubts, contact me. This is simple things. You can just do this also, this only. Okay, please practice. So now we get something A0, A1, A, B, C. That are the coefficients in the first column. Please check the first column, A0, A1, A, B and C. That is the important thing. That first column values are the one and only important thing for inspecting the stability. First column elements A0, A1, A, B, C. Please check those values. At present we can check. If it is not values like A0, A1, if it is simple numericals, we can easily check whether it is positive or negative. That is the important thing. For stability, there should not be any sign change in the first column. That is, if A0 is positive, A1 should be positive, A should be positive, B should be positive, C should be positive. Or otherwise, all the terms should be negative. Then there should not be any sign change. If A0 is negative, A1 should be negative, A should be negative, B should be negative, C should be negative. Otherwise, if there is some negative and some positive, there is a sign change. If there is sign change, the system is unstable. If there should not be any sign change in the first column, for the system is stable. That is the concept of RH stability criteria. Now we are moving to a simple problem. Transfer function 10 by s3 plus 6s square plus 11s plus 6. Test the stability of the system. So its denominator is s3 plus 6s square plus 11s plus 6. Equating that equal to 0. That is the characteristic equation. You can see in the red ink. That is the characteristic equation. So before applying RH criteria, check that two things. Is there any sign change in the characteristic equation? No. S cube's coefficient is positive, S squared's coefficient is positive, S, that's coefficient 11 is positive, S raised to 0, its coefficient 6 is also positive. So no sign change in the characteristic equation. Is there any missing of coefficient? No, it is a third order system. S cube is present, S square is present, S is present, and the constant is also present. So no missing of coefficients. Now draw the RS stability criteria. In S cube's row, you have to write 1, 11 and 0, because 0 means there just after one alternate position no coefficients are there, no S term is there, so you have to take 0. So 1, 11 and 0. Yeah. In S square's position, we have to take 6 and 6. Yeah, 6 and 6. 6, 6 and 0. You have to, it is better to put 0 in the last one. If coefficients are over marked completely, fill the third column also with 0. That will make you easy for while doing calculations. You will get, it will avoid some malcalculations. Okay, now find S raised to 1. It is simple. S raised to 1, how you will get S raised to 1? 6 into 11 minus 6, 1 into 6. 6 into 11 means 66 minus 6 divided by 6. Yeah, 66 minus 6 divided by 6, that is equal to 10. Now, what about the second element in this position? What about the second element? You have to do 6 into 0 minus 1 into 0 all divided by 6. Anyhow, it will be 0. And third element, so we know that it will become 0. If you want to check also, anyhow it will become 0. Now you have to find the corresponding row for S raised to 0. So for S raised to 0, first element will be 10 into 6 minus 6 into 0 divided by 10. 10 into 6 means 60 minus 0 all divided by 10. That will give 6. 60 minus 0 by 10, 6. And the other one, definitely it will become 0 because you can see 10 into 0 minus 6 into 0. Don't need to calculate, it will become 0. So this is the case. Now please check the first column elements 1, 6, 10 and 6. 1, 6, 10 and 6. Is there any sign change? In between 1 is positive, 6 is positive, 10 is positive, 6 is positive. No sign change in the first column. So please read it. No sign change in the first column means no right side poles. Right side poles is equal to 0. If there is one sign change, there should be one right side pole, like that. If there is two sign change, two right side poles are present. For the time being, we are not having any sign change, so number of right side poles is 0. So now itself we can say system is stable. But there is one twist. Can we simply say the system is stable? Okay, there is no right side poles. But if there is some poles on the imaginary axis, system is not simply stable. System will become marginally stable. So we have to check that also. Anyhow, it is a order of the system is S cube. It is a third order system. So at least we will get 3 poles. We will get 3 poles. Total number of poles is 3. And okay, before going to this step, you please read this one. If any row is a 0th row, then there should be poles on j omega axis. That is an important thing. In this problem, we know that there is no 0th row. Is there any 0th row? If 0th row means all the elements in a row should become 0. Here also we can see the first element is non-zero. Here also we can see first element is non-zero. So non-zero elements are absent in the present case. But if there is any non-zero row, definitely, if there is any zeroth row, here all the rows are non-zeroth row. If there is any zero row means all elements should be 0, then for the transfer function there should be some poles on imaginary axis. For the time being, we don't need to check whether that is there or not because all the rows are non-zeroth row. So there is no poles located on j omega axis or imaginary axis. So please read this. If any of the row is a zeroth row, then there should be poles on j omega axis. But in our case, number of poles in j omega axis is 0 because in our case, all the rows are non-zeroth row. Zeroth row is absent. So what are the points we get? Total number of poles is 3. Poles on the right side is 0. Poles on the j omega axis is also 0. Then what about the total number of poles on left side? All the poles should be there on left side. So total number of poles on left side is equal to 3. So after this first point, total number of poles is 3. You have to check total number of right side poles is equal to 0. And then you have to check this one. Is there any zeroth row? No means there is no poles in j omega axis. Then you have to write total number of left side poles. That will make more sense. So total number of left side poles is equal to 3. So what happened? You can comment about the stability and you can also say where the poles are located also. But you didn't solve the characteristic equation. You didn't find the actual value of poles. You didn't do the response analysis. Without having this whole, you can simply find the position of poles and you can comment exactly about stability. That is a strength. So this is the second question we are practicing, and this question is a fourth order system. So please check the denominator of transfer function. 2 into s raised to 4 plus s cube plus 3s square plus 5s plus 10 is equal to 0. So the order of the system is 4. So characteristic equation is denominator is equal to 0. 2s raised to 4 plus s cube. Okay, the denominator will be equal to 0. So that is the characteristic equation. So before going to R stability criteria, first we have to check two conditions. First condition, is there any sign change in the characteristic equation? No, all the coefficients are positive. So that is satisfied. Second condition, is there any missing of coefficients? That is also no. All the coefficients are present. S4, S cube, S square, S raised to 0 constant. All are present. So now we can arrange this into tabulation chart. So the higher order is S4. So I write S4 here, S cube, S square like that. So on. And now 2 is the coefficient of S4 and alternatively 3 is coefficient of S square and 10 is coefficient of S raised to 0. So I written these 3 coefficients in first row. So you can see 2, 3, 10 here, 2, 3, 10 here. And alternatively 1, 5 and 1, 5 are the alternate coefficient, and for balancing it, S0 is also put in the last line, 1, 5, 0. Now S4 and S cube are, S raised to 3 are okay. Now we are going to find the term related to S raised to 2. So for finding that, we know that 1 into 3 minus 2 into 5 by 1. That is the thing. So 3 minus 2 into 5, 10 by 1. 3 minus 10 by 1, that is equal to minus 7. And for the next value, we have to do 1 into 10 minus 2 into 0 by 1. That is 10 minus 0 by 1, that is 10 itself. If you want to find the third value in the column, no need to find from the vision, from the primary inspection itself, we can see it will be 1 into 0. There is nothing there in the right side. So 1 into 0 minus 2 into 0. Anyhow, it will become 0 only. So third row is also okay. Now we will check the fourth row, S raised to 1. That is nothing but minus 7 into 5 minus 1 into 10 by minus 7. That is minus 35 minus 10 by minus 7. That is minus 45 by minus 7. So it will give plus 45 by 7. And the second value, we can see the 0 here. Let us check whether it is 0 or not. minus 7 into 0 minus 1 into 0. Anyhow, this value will become 0. And also consequently this will be also equal to 0. So the s raised to 1, that row is also completed. Now what about the last row? We can check from here itself. 45 by 7 into 10 minus 0 divided by 45 by 7. So that value will be plus 10. Yeah, you can see plus 10. And after that, all the values will be 0. You can check. Now, please check the first column. 2, 1, minus 7 plus 45 by 7, 10. How many sign changes are there? All of you, please answer. How many sign changes are there? 1 or 2? That's my question. Normally people will say 1, like you said, 1. But it's not 1. From 2, we can see 2 is positive, 1 is also positive. 1 to minus 7, that is a change. And again minus 7 to plus 45 by 7, that is another change. So 2 changes are there. That is, if this value is also minus, what happened? Suppose this is minus and this 10 is minus. What happened? How many sign changes will be there? In that case, there will be only one sign change. But here, from 1 to minus 7, it is a sign change, and minus 7 to plus 45, 7, it is another sign change. So we are having 2 sign changes. That is the logical thing we have to understand here. Okay. So we can mark a column related to that also. Sign of first column elements. You can write like that also. Sign of first column elements. Plus, plus, minus, plus, plus. That is the thing. So here, this is the first change. This is the first change, and this is the second change. This is the second change. So 2 changes are there. So number of poles in the right side will be 2. Let us check. Number of sign changes in the first column, 2. So number of right side poles, that is also 2. What is the total number of poles? The order is 4, s raised to 4. So total number of poles will be 4. Number of 0th row. Is there any row 0? Please check. Is there any 0th row? No. All the rows are non-zero rows. So number of 0th row is equal to 0. So number of poles in j omega axis is also 0. So no poles in the right side and no poles in the j omega axis. So what will be the total number of poles? Total number of poles is 4. So what will be the number of poles in the left side? That is also, oh sorry, I made some wrong comment. Total number of poles in the right side is equal to 2. Okay. Number of poles in the j omega axis is equal to 0. Then what will be the number of poles in left side? That is equal to total number of poles minus poles in the right side plus poles in the j omega axis. That is 4 minus 2 plus 0. That is equal to 4 minus 2. Answer is 2. Number of poles in left side is equal to 2. Anyhow, there is some poles or 2 number of poles in the right side. Even if there is a single pole is on the right side, the system is unstable. So we can write the system is unstable because 2 poles are there in the right half plane, RHP. So hope you enjoyed this session. This is a very important session for exam point of view. So be very strong in the concept of RH stability criteria. We'll see in the next class with special cases of RH stability criteria. That is also very important for you for exam point of view. So thank you for watching. We'll see in the next class. Okay, thank you.